Can you see it?
Yes, it is perfect, sir.
Okay, excellent.
And open the chat window also so that you can make interaction with the participants.
Yeah, sure.
Can we start, sir?
Okay.
Yeah, just I introduce you. Then
Yeah,
after
sure.
we will start, sir.
Okay,
So,
sure.
very good afternoon to all. After the great lunch at your home, today we have great privilege to have Professor Ibrahima Faye sir with us. He is currently working as an associate professor at University Technology of Patron, Malaysia. He is associated with the Department of Fundamental and Applied Science and the Center for Intelligent Signal and Imaging Research. He received a BSc, MSc, and PhD in mathematics from University of Toulouse and PhD in MS in Engineering of Medical and Biotechnological Data from École Centrale Paris. His research includes signal and image processing, pattern recognition, and engineering mathematics. He is a senior member of IEEE and he has a very good Google Scholar citations, which is more than 2000. It is a great privilege to have you with us in the FDP. Now I welcome you all in the Bharati Vidyapeeth Institute of Computer Applications and Management. Welcome, sir. So
Thank you
now
very
I
much.
request you take over the session and enlightening us upon the progression from machine learning to deep learning in medical image analysis. Sir, please.
Thank you. Thank you very much. Thank you for the introduction. Good afternoon to everyone. Actually, I'm very happy to be here. Would like to thank all the organizers, including Prof. Huda and the team. So my topic is progression from machine learning to deep learning and applications in medical image analysis. So as I know that probably not all of you are in this area of image processing, or in particular in medical image processing. So I will be going slowly, and those who are like expert in the field have to bear with me for a while, just to make sure that everyone could follow the trend. But before going through the slides, let me just this is just where. So this is India, and I'm somewhere here in Malaysia. Okay. As you know, Malaysia has two parts. So if you zoom in, you have the two sides of Malaysia. So Kuala Lumpur is the capital, and our university is somewhere near Ipoh. That means towards the northern part, going to Thailand. Okay, so that's for our university. Now, for the topic, this is what I would like to cover. We have the traditional machine learning techniques. Then the second section, I will talk about neural networks. What is convolutional neural networks? And from these basic definitions, what people have been doing, what are the architectures and the methods that have been developed in this area. And the last part will be the application. So we'll be showing a few applications. And for some of them, you see the difference between the traditional machine learning and then what were the changes when deep learning was implemented. Now, as I mentioned, I would like to start with very basic things. So I will start with something which is not even in the medical area. So we just imagine that you have a bag having some fruits. Let's say we just have two types of fruits. We have oranges and apples. So without looking at the fruits, we'd like to differentiate them. Okay. So for example, in the first case, let's suppose that we cannot see them, but we can touch them. So if we are able to differentiate these two fruits just by touching the fruits. Another way of doing the same thing, let's say now I cannot touch them, but I will know the weight. So I know the weight of the fruits. I would like to know if I could differentiate these two types by just using the weight. And one more will be, for example, by just the smell. So I cannot touch them, I cannot see them, but I can just have the smell. I can smell them. So based on the smell, will I be able to differentiate these two fruits? So this is the basic problematic machine learning, let's say, of classification. Go back to these terms later on. But that's the main idea, how to differentiate things based on some tools that I have. For example, here could be by the touch, could be by the weight, or could be with the smell. Now, the one way of defining machine learning techniques, so algorithms or models used for a computer to perform a specific task based on some patterns. So this will be reflected later on. But if you just look at the previous example, we need to look at some patterns depending on which of them that I have access to. And from there, we have to decide it has to be done automatically. So that's the one of the ways of defining machine learning. Now, you may have different problematics. Let's say the first one, we talk about supervised learning or classification. So for supervised learning, let's say we have attribution of a class. So this class will be defined, we'll have a data set. A data set is provided. For example, some specialists have graded some medical images. So we have this as a ground truth. Now, what we want to do, we have to make a model so that if I get any new image, I will be able to do the classification, but based on what I already have from the data set. So this is the most classical problem that we are dealing with this in this area. Okay, so classification where a data set is given, and from there we want to build a model. There's a second problematic, which is the unsupervised learning or clustering. So this time I don't have a data set. Let's say it's something totally new. I would like to know how to cluster, for example, the data. How many groups are there? I have to find it because from the, let's say I don't have any data set or any specialist person has made the classification or had made the different groups that are there. So one example of this we'll be seeing later on. In some medical images, I would like to do segmentation. If I want to do segmentation, I may not know how many groups, how many classes are there. So that becomes a kind of clustering if I don't have any labeled data given, let's say, by a specialist. And in between, you will have the semi-supervised learning. So we have a small data set, which is labeled, but then it doesn't necessarily represent all possible cases. So when I'm doing the learning, when I do, for example, doing the testing, I may have the same that I have in the small data set, but I may have new patterns that are not in the small data set. So then it becomes a semi-supervised learning where we may have to discover new patterns, and as well we have to consider what the patterns that we already have. So these are the classical problematic that are solved in this area. The first one being the most common, which is the classification, where you have a certain data set, and from there you need to make a model to be able to classify new data. Okay, some of the tools that are used, the main tools, actually, the first one will be the feature extraction. So one way of defining it is a transformation of input data into a set of features. So what are the features? It could be any characteristic, any attribute of the object I'm dealing with. For example, from the previous example, we have like the weight could be one feature, the color could be one feature, or the texture of the skin could be one feature. Now, if I have many features, if I extracted many features, not all of them could be good. So depending on the problem that I'm dealing with, I may need to look at the very specific features that will fit the problem that I'm solving. So that's why we're talking about feature selection. So I have a set of features, but not all of them are good. I would like to extract some of them, the most selection some of them, the most suitable for the data I'm dealing with. Just to illustrate that case, I will go back to the same example just now. Here we have, let's say, a bag with oranges and apples. So over here, if I use the touch, which is just looking at the skin smoothness. For example, for an apple, it will be smoother compared to the orange, which will a bit rough in terms of the skin. So for this particular case, using the skin texture could be a good feature to differentiate these two objects. But if I use the same feature, if I go from, for example, over here we have oranges and mandarins, this feature might not be that good because these two fruits still have roughness in terms of the skin. Okay? So this is just to illustrate that depending on what I'm trying to solve, I need to figure out what are the best features that will fit the point I'm dealing with. Now, for that, I will just go through some of the classical methods, some of the feature extraction or selection methods. Okay? Now, we start with the first order statistical features. So let's say we have an image. So we could look at an image just as a matrix. Okay? So I have a matrix. The size will be, let's say, X and Y. And in each pixel, I will have a value, which is the gray level. Okay? So we could define, let's say for that matrix, PL, which is number of pixels with gray level L, L being, for example, between 0 and 255, and divided with the total number of pixels in the image. So it will be like a probability. Okay, I will have a ratio. So the number above will be always smaller than the number below. I will have a probability. So we can look at this as a random variable. So we can say that this is a first order histogram. So we could use it as a way to differentiate different images. Because once we have it, we could extract some statistical features. For example, I just calculate the mean. If I look at the image, what is the mean of the gray levels? Another one would be variance. So all these statistical values will be just calculated from the image itself. And some other, if you go a bit further, we have the skewness, and then we have the kurtosis. We have some formula we could just implement, and we can get for each image, we could get a value, or let's say a set of values representing that particular image. Now, just to illustrate that it could work, for example, here we have two different images. This is just representing a forest, and this is the cameraman. So if you look at the histogram, definitely there's totally different patterns. So this could be a way of differentiating different types of images. Okay, so that's the first order. Now we could move to second order. We would like to get something a bit more specific. So we look at the image, again, having different gray levels at each pixel. So we'd like to define a matrix P of theta D with L1 and L2 being two different gray levels. So for that, we could define, for example, theta would be the angle. So we are looking at horizontal direction. We could look at 45 degrees, 90 degrees, 135 degrees. And the D here represents the neighbor, the distance between, if I look at the pixel having L1, if D equals to 1, I'll be looking at the next one, the close to it, okay, then the closest neighbor. If D equals to 2, then I look at the pixel which is 2 away from the pixel I'm looking for. And same thing, Okay, so we'll show it later in the next slide. So we could look at the P theta D, which will be obtained, which will be the way of finding the gray level co-occurrence matrix, which is something that has been used a lot in medical image processing. Okay, so just to explain what I was mentioning in the previous slide. So let's say over here I have this image. These numbers, let's say they represent the gray level. Okay, so I'm looking over here at, for example, distance equal to 1. That means when I look at this pixel over here, I will just consider the neighbor, the right neighbor. That means the distance is 1. And if I just look at the neighbor in the right side, that means I'm considering that theta equals to 0. Okay, remember that we have two parameters. We have theta, and then we have d, which will be the distance. So this is just to illustrate. If I look at distance equal to 1 and at theta equals to 0, that means if I have 1 here, I will just look at the next, the value that I have in the next pixel. So over here, if I look, for example, the number of cases where I have 1 and I have 1 at the right pixel at the same level, then I just count it. So over here, I only have only 1 cases where I have 1 followed by 1 in the direction of at 0 degrees, and just distance equals to 1. So then I have to store in this matrix 1. Another example, if I look at all the cases in this matrix where I have 1 pixel at 1 and the neighbor at the right side at the same level to be 2, I only have this case over here and this case over here. So I have two instances in this matrix. So then in the intersection 1 and 2, I will have to store 2, okay, and so on. So I will just look all these pixels, and from there I will generate a matrix. Now, you may say, well, if I have an image, this is not necessarily the size. It could be, for example, 256, 256. In that case, what is done is we do the quantization. So we want to, for example, bring all the pixels between 0 and 15, we give it to 1. And then from 16 to 31, we give it to 2. That means we do a quantization. The matrix that we have at the beginning representing the image, we just reduce it to a smaller matrix. And this one is needed because otherwise the GLCM that we will obtain here will be too big. Okay? So that's the idea. And it is somehow proven that we don't lose a lot, although we have some loss will be there because we are of the quantization. So at the end, you get this matrix. And this is for theta equals to 0 and the distance being 1. We could do that for any other angle and then any other distance. So once we do that for the right side, we could do the same thing from the left side. So that means looking at the pixel in the left side. Okay? And we could do the symmetrical. That means just combine these two. Either we divide by 2 or we just add them to make it symmetrical. And we could as well normalize. And that will give us this matrix P of theta D, L1, L2, representing the image that I'm dealing with. Now, what can we do with this? Again, we can find some features, some statistical features. Okay, so we have a few of them here. For example, the ASM, which is the angular second moment, which will just represent the smoothness of the image. So we have a formula that we could use and then calculate it for each matrix. Similarly, we have the contrast. Okay, again, we have a formula for it. So local level variations. Actually, there are more than 14 in the initial paper regarding these features, but the most commonly used are these 4 that I'm showing here, actually 5. We have as well the correlation. Okay? So it represents the relationship between the gray levels. We have the homogeneity. Again, we have a formula based on this P of L1, L2. We have the entropy. So once we calculate these features, that means now every image could be represented. For example, if I just use these 5 features, every image will be just represented by these 5 images. Okay? So that could be the way of seeing if you can differentiate them based on these features. Okay, so that is the features that we could extract from the image. either first order or second order. Which, yeah, we have some formula to implement, but it's not that complicated. As long as we have the formula, we can just get them. If we want to move further, we could look at Fourier analysis. Okay? So we analyze the signals, for example, or the images in the Fourier domain. So we'll get, like, for Fourier series, we have a decomposition into k frequency components, with k being integer. And if you go further, for any signal that we get, we could use the Fourier decomposition or Fourier transform. So we get a decomposition by using lambda frequency components. So lambda could be a real number, will be a real number. Now again, that means I could represent the signal that I have or the image that I have with a certain number of values that could be used for making the difference between them. Okay? So that could be the amplitude, for example, amplitude or the spectrum. So it looks again somehow simple, but it could be a good way of differentiating. For example, if I have two groups, some signals where the amplitude is very low, some others the amplitude is very high, I just need, for example, to set a threshold, and the threshold could be good enough to differentiate the two groups. Okay, so that was for Fourier analysis. Next one will be wavelet analysis. These are all somehow classical ways, but they have been used so many times in this area. So they are part of this these steps for doing image classification, for example. Now, it's just to simplify, but let's say if I have a signal, the wavelet could be seen as just a way to look into the different patterns that I have in the signal. So, for example, we can represent it as a way to decompose, and it's just like I have a grill that I just put on the image. So I want to see the details. If I want to get finer details, I need to go to the next level, a bit finer. So we could see it that way, or we could say the basic thing is that if I use Fourier analysis, I will have the spectrum, I will have the amplitude, but I don't know where it is happening in the signal. But wavelet will solve this problem because we know exactly at each point what is happening in terms of the amplitudes and the spectrum. So that's for signal. But if you have an image, we could look at it as a composition of signals. So we look at an image as a function in L2, R2. At the end, we can use the decomposition based on some wavelet and the wavelet functions. So we could decompose the image as a function, and at the end we can represent it as a set of numbers. So these are, for example, the decomposition in terms of approximation, horizontal, vertical, and diagonal. Okay. This is just when I look at the image, I look, for example, in one direction, I consider it as a signal. If I do for another direction, it will be another signal. I do the decomposition, I could get the vertical decomposition, horizontal, diagonal, and then I have the remaining, which is the approximate. At the end, if I have the image, I could set based on the wavelet I'm using for the decomposition, I will get a set of numbers representing this signal or this image. Now, what can be done with this? So we could, when we do the extraction, so we have the coefficients. The coefficients will be representing the image. That is let's say, the extraction. I could, for example, select just some features. Okay? For example, looking at the set of the largest coefficients that I have from the wavelet decomposition. Or I could look at the statistical features, the same statistical features, for example, the mean, the variance. Instead of using them from the original image, we use them on the wavelet coefficients that we have obtained after the decomposition. Okay? And we could as well look at the statistical features of the wavelet coefficients, but at each level. So we have level 1, level 2, level 3. At each level, I could find the coefficients, do some statistical analysis, and then add to the next level, and so on. So that could be representatives of the signals or the images. So just to illustrate, if we use the previous images, that was the cameraman and the forest, by doing the wavelet decomposition and looking at the largest coefficient, 100 coefficients over here. We just represent them. So definitely, it could be a good way to differentiate these two images. Okay, so after wavelet, the mathematicians moved to higher order. So we talk about ridgelet, and then we talk about curvelet. So ridgelet is mainly you are looking at, it's like you are zooming in, but you look at the curves are straight lines. So if I have a curve, if I zoom in, yes, locally it could be like a straight line. So this is one way of looking at images where you may have not really straight line, but something that looks at straight line. It could be a good way to differentiate them. And the next one was the curvelet, where now instead of looking at zooming in and considering the curves as straight lines, we look at the curves as the curves are they are by adding just an angle to show how the curves are represented in an image. And so there are many more have been developed, but the principle is exactly the same. If I have an image or a signal, if I do the decomposition, I will get a set of coefficients. So these coefficients will represent my image, and I could use it for the next steps. Now, this is extremely important to know what are the tools that I'm using based on the problem I'm dealing with. So just to illustrate that, there's one example over here. The same thing as just now, when we want to differentiate between, for example, oranges and mandarins. I know that if I use the skin smoothness, then it may not be that good. So similarly, this is an image. This is it's not a natural image. It was just a simulation where small dots were simulated as well as straight lines. Okay? Now, over here, what was done is that you do the decomposition using wavelet. After doing the decomposition, you just remove all the small coefficients and then do the recomposition. So once you do the recomposition by using wavelet, then you obtain this image. Which means if I'm interested in these small dots, the wavelet will be good enough because it gets me rid of all these straight lines that I don't want. Another example, the same image. Now we use decomposition with ridgelet. So you get a set of coefficients. The small coefficients, you set them to 0, and then you do the recomposition. So when you do the recomposition, now the small dots are not there, but we can catch the straight lines. So this is extremely important, means depending on what are the types of objects that I'm trying to classify or I'm trying to detect in an image, I need to know what are the appropriate features. Okay, so this is, we cannot just use any of them randomly. We need to understand what they do and how they are created and which kind of pattern they could detect. Okay, let me just check. I think there were some questions. Okay, so for ridgelet, as I mentioned, actually it is able to detect the straight lines, the straight lines. And how it is done is just if you do a decomposition, for example, using Fourier analysis, you could combining different, for example, different patterns. You are able to look at the curves are locally are as straight lines. So in that case, ridgelet will be able to find it, to detect all the straight lines. And this is what is illustrated over here. If you do decomposition with ridgelet and we remove all the small coefficients, when we do the reconstructions, we can find out all the straight lines that were in the image. Okay, so that's for feature extraction, which is one of the first thing that is done in building a model. That means we need to find the good features, and the next stage will be how to do the classification. So I use the given data, for example, to build the model to find the good features, And then next step will be to do the classification. I have to use a classifier. And then if I have any new image or any new input, then I have to use the model to decide what is the class in which it belongs to. So again, this is one of the classical classifier, which is the k nearest neighbors. So for each data to classify, calculate the distance between it and the data in the training set. So from there, we can classify the input data based on the most represented class among the k nearest neighbors. So one way to illustrate this, for example, if you are dealing with two classes, I have two classes. This is from, let's say, the training set. I have the squares and the circles. And this triangle, the yellow triangle, will represent a new data. Now, from this new data, I will just calculate distance between the new data and the points that I have in my training set. So if k equals to 3, I just look at the 3 closest data that I have in the neighborhood of this new data. And then I would look at the majority. So over here, I will have 2 squares. I will decide that this new data actually belongs to the class of the squares. Okay, so it's very somehow simple and straightforward, but still well used because it works in some cases. The challenge sometimes would be how to find the good k that works very well for the data that you have. Okay? Sometimes it's just there's many improvements that have been developed, but sometimes you just have to do it by testing different values and see which one will give the good results. Okay, so it's one of the classical ways. It has some advantages in terms of computations. It's relatively fast, and for a data which is not that complicated, it could give very good results. Another popular classifier is the SVM, okay, those support vector machine. So this is just to explain the principles of this this classifier. It looks at optimal hyperplan to linearly separate two classes. So again, I have a training set. I have two classes. I'm trying to find a line in between, and that could separate the two classes. If I take this line, well, it is separating, but is it good enough? Probably no, because it is closer to this border point, and same thing is closer to this border point. So we would like to find a line which is the further possible from these two extremities. So we want to maximize the margin. So that's the basic principle. We look at the support vectors, those at the extremities, and then we want to find the line that is the best in terms of making the difference as far as possible between the two support vectors. Now, one way of defining it, we have from the training set, we have a set of values, let's say xi and yi. Yi, this is a two-class problem. That means yi will just have two values. It's either -1 or 1, depending on which class it belongs to. Okay, and x1 up to xn will represent the training data. So we could define h as the set of all the z where w.z minus b equal to 0. So we just do the dot between the two, dot product between the two vectors, and then minus b would be just the offset. That means where we are getting, because this is like equation of a line. So first we define this space, okay, where w is the normal vector to the medium line. So if we take the medium line, the normal vector would be somewhere over here. So we could define this space. And we could define as well h2 and h1. So for example, if we say wz minus b equals to 1, it will be represented by representing one of the classes, and h1 will be another class. So we have seen that yi is either -1 or 1. So we can define the set h1 and h2. Okay, that in that case, we can say that zi belongs to hi, where I could be either 1 or 2. Now, what we are interested in, we want to maximize the difference between the distance between the two plans. If I go back for a while, I have defined these two lines. I want to maximize this distance. I want it to be as far as possible. That means I need to find the best lines that will give the distance which is the highest. So we can just find the distance between H1 and H2 by using this dot product. This is just the unit vector because we divide with the norm, and we do divide dot product with Z2 minus Z1. After doing some simplifications, okay, by using these definitions, WZ minus B equals to 1, or it is -1. So by using this definition, we could come out with the distance between the two plants to be 2 over W, which means now I need to find what is the W that will give the highest value for this distance. So that is the basic principle, but at the same time, we don't want to have any point in between. So we need to make sure that there will be no point in between, because that will make challenging for the classification later on. So we want to make sure that nothing is in between. So that is why we have to add some constraints. The constraint is that Wxi minus b is greater than 1 will be class 2. We want all the points of class 2 to be beyond the line, not in between the two lines. And same thing for the second line with the second class. We want this inequation to be valid for any value of any point in the class 1. So when we combine these two, we could write it in just one inequation, because the yi is either 1 or -1. So we can, if you multiply with -1 over here, we are just changing the direction of the inequality. So we could write one inequation representing these two. And then we have to optimize, or we have an optimization problem with a constraint. Okay. So we have this value that we need to maximize the distance, and we have these constraints. So when we maximize this distance, actually it just comes out, it will be the same as just minimizing the norm of W using the same constraint. Now, this optimization problem with constraint, classically it is solved by using the Lagrangian multipliers. I did not add all the details over here. I don't want to bother you too much. But once you solve it, then you are able, for example, to set a decision rule to say that if I have any new data, U, from the W that I obtain from the optimization, I just need to find this difference. If it is greater than 0, then would, for example, say that U. Okay, so that is the classical way if I have something that could be separated by a line. But this is just to illustrate that it may happen that you cannot find straight away a line to separate the data. Okay, this is a typical example where here I have two classes, the red and the blue. Over here, definitely I cannot use one line to separate the data. But using the kernel trick, so we can somehow transform this space by using this function and make it in a way that now I could separate them with a line. So this is why the classical SVM, which works for line, by adding the kernel, you can apply it to some data that are not really at the beginning separable by using lines. And this is just a few examples of kernels. Again, it's not easy to know which kernel you have to use, because you sometimes you don't have an idea about the setting of the data. I mean, how the data looks like. So if you have an idea, then you could decide which one to use, or you have just to try a few of them to see which one works very well to separate the data. Okay, let me just check the chat. There are some questions.
So there are few questions, sir.
Yes. Okay. Is SVM useful in multi-class problems with around 35 classes? Yes, SVM can be applied in multi-class. One way of doing it is, for example, I will just talk about, for example, 3 classes. But if I have more than 3, it works the same way. So what I could do is, if I have 3 classes, let's say I have A, B, and C, the first step will be to do the 2-class SVM classification by using, for example, A against B and C. Okay, so I could differentiate A in one group and B and C in another group by just using the the SVM two classes. And then between B and C, I will apply it again. So it's just like making a loop. So that means if I have 35, I could do it. Definitely, it will be a bit lengthy, but I could apply SVM many times and to differentiate one against the other. And from the group remaining, I will apply again once against the remainings until I obtain a multi-class SVM classification. Okay. So this is just two
So
illustrations.
there is another question.
Okay.
Wavelength gives information about the time frequency domain. What
Yes, I think I already.
information you have covered?
Yes, I already covered this
Okay,
now.
okay,
Previously,
fine, sir, fine.
this one. Yeah, yeah,
Thank
yeah. Okay, okay, thanks. Okay, so these are the 2 classifications. They are somehow famous classifiers. There are definitely many more, but just wanted to illustrate some of these 2. Now this is the whole picture. I have feature extraction methods. I just highlighted some of them, but definitely there are many more. Well, for example, LBP, HOG, SURF, and etc. Okay. And in the other side, we have the classifiers. So for example, here we talked about SVM and KNN, but we have the neural networks, we have random forests, we have too many. So what is done is you need to find the right features, okay, by selecting over here. And once you get the right features, again, you need to check what is the right classifier. So that's why sometimes it works, sometimes it doesn't work, in the sense that, or at least we don't know which one works the best in general. In some particular cases, we can guess the best feature extraction method, for example. But in general, it is quite challenging to know what is the best. But that's the overall picture, finding the feature extraction method and then finding the classifier. And from there, you can build your model and see how it works. Now, once you have the model, definitely you need to check the performance of it. So we have over here, for example, what is a true positive, a true negative, false positive, and then false negative. I will probably give an example in terms of medical. Okay, it's probably the best in this case. So true positive, you have a system. Someone comes in, the person is sick. I mean, you have the data of the person. The person is sick, and the system finds that the person is sick. So this is a true positive. The false positive, you have the data of someone who is healthy, and the system says actually the person is sick. Okay, so that's false positive. And true negative, the person is, let's say, healthy, and your system says the person is healthy. So it's a true negative. And the false negative, let's say you have a person who is sick, who is not healthy. He comes in, or she comes in, and your system says that the person is healthy. Okay, so these two are big issues in medical. Between false positive, that means you are saying to someone that he is sick, but actually he is healthy. Or false negative, you are saying to someone that he is healthy, but actually he is sick. Now, I would I don't know if I can have not sure if there's a way to do a poll, but I would like to ask, which one do you think is the worst between the false positive and false negative? If you could have just 2 or 3 answers. In terms of medical, which one is the worst one? Yes. Any guess? Any guess in the chat? Yes, definitely yes. False negative will be the worst scenario, because false negative, the person comes in and your system say you're okay, you're fine, you can go home, but the person is sick. That means the time he comes back or she comes back, it will be at a stage which will be probably worse. Okay? The first one as well is bad, but it's not too bad compared to the false negative. False positive, you are saying to someone that he's sick, but actually he's not. So psychologically, it could be a challenge, but definitely yes, false negative is the worst scenario. Thanks. Now, from there, the classical reports will be the accuracy, but for people who are in the field, they know that definitely people need to know what is the sensitivity of your system, sometimes called recall, depending on the area in which you are working on. And then we have the specificity and some other terms like precision and then the F measures. So once you have a system, you want to check about these evaluations, I mean the performance of your system. Okay, I think that is all for the first part, which is the traditional machine learning techniques. What we want to do next is to zoom into the neural networks, and then we will go into the CNNs. Now, the classical way of representing them, because they are just coming, the idea is coming from the biological neuron. So I have a set of input, let's say x1 to xn. I will have some values over here, which are, we'll see later on, they are the weights. I have a combination of this. That means, for example, if I have in the brain, I have some synapse, I have some signals coming from different ways. If I combine them with some values, some weights, and at the end, I will be getting the output, okay, from the combination of all these inputs with some weights given. And I may have a constant, which is the bias, which is B1 over here. We'll have as well a function G. We'll see later on what it represents, but that's the overall picture. So we could have a neural networks where we have inputs, we have combination depending on where we are going and the weights that are used. We could apply some functions. At the end, we have the output. Let's say over here we have O1. Okay, so these are the inputs, xi's. We have the weights. We do a combination, the sum for all the i's, and then we add a b, which is the neural bias. So we could write it in matrix form in this way. Okay, so the output will be a function a of x. Now, when we activate, we have to apply one function g, which is called the activation function. We'll see some of them. At the end, we have the activation applied to ax, and we could call it the hx, which is what we are getting at the output of your network at the particular node. So if I have the same principle continued, for example, I start over here, I will have the weights and so on from different nodes. I will apply a certain activation function over here, and this will be my output at the first level. But then I could continue the process. Okay, apply a new set of weights, apply a new bias, and then calculate for the next level, and so on. So we could have the depth, which is how many layers we have there, and then the number of units, which will be the width of your network. Okay? But the principle is exactly the same. We need some weight, we need some bias, and then we apply an activation function, and we could keep doing it until the end for our final output. Now, this could be used as a classifier for neural networks. Could be done, for example, for multi-class, not necessarily two class. It could be more than one class. So we could have multiple outputs. So the key point over here is we want at the end to get something which represents the probability. For example, if I have two classes, I would like to get a probability of the input data to belong to class 1 or class 2. Okay, so my output should be 2 values, and then I will look at the highest probability, and I will classify accordingly. Now, the classifier function for doing this is the softmax, which is defined as exponential. Let's say if I have two values, only A1 and A2, the softmax at A1 will be exponential A1 over exponential A1 plus exponential A2. And softmax for A2 will be something similar, exponential A2 over the same sum. So since these two values are all positive and the numerator is smaller, what I will be getting will be less than 1. Okay? So it is just kind of probability. So we can use it for classification by classifying where we have the highest probability. If I have more than 2 classes, it still works the same way. The sum of all of them would be 1. So each of them will represent a probability. Then I could classify accordingly. Now, the training, how it works. So I have a training set. I know, for example, at the beginning from my training set, I know what are the classes of all the objects in my training set. Okay? If I have, for example, 2 classes, let's say healthy or sick, then from each data, I know that one belongs to healthy or sick. Okay. So we could start with some weights, and then we just apply some activation function, and we run it for a certain number of layers, for a certain number of layers. And at the end, when we use the softmax, we could get a probability at the end. If I just have 2 classes, then I will have 2 values. But now I know from the the training set, I know what are the classes of these elements. So I could compare what I have in the training set and then what I obtain from this neural network. So I could see if it is well classified or not. So I could compare the prediction with what I have in my training set. So at the end, when I get the values for the output of this neural network, I need to check, I will need to compare with the classes that are given in my training set. So there's something called the cost function. That means how far the values I obtain from my training are from the values in the training set. I need to evaluate this, and I need to make the error as small as possible. Okay? So this is something that we need to optimize. Okay, so as mentioned over here, definitely the output will depend on the input X and the weights, because all these parameters could be set randomly at the beginning, and then we see later on how to improve them in terms of getting a better output. Okay, so the whole scenario will look like this. So this is the input. We just do the forward propagation, just applying some weights. Could be randomly set at the beginning, some bias at different levels. At the end, we get the softmax, and then we get some probabilities. So we look at the difference between the values that I obtain in terms of class and the values that I should obtain based on the training set. Now, that error, I need to minimize it. I need to make it as small as possible. And when we talk about minimization, we have to think about the gradient. So this is a function. I will take the gradient, and I will use the gradient to do the backpropagation. So backpropagation, I need to go back, and I have to rectify all the, not rectify, but to improve the weights that I have based on the gradient that I have over here, then over here. So this looks complicated, but actually it's very simple in the sense that you just use the chain rule of calculus. Because what is happening is that I have, for example, z is a function of y, but y is a function of x. So at the end, if I want to differentiate z in terms of x, I just have to use the chain rule. So which means if I'm at the end of the network, we go back for a while, this gradient, I will be able to calculate it based on the parameters that I have right before. But the parameters that I have right before, they are depending on the parameters before. So by just doing the chain of going back, which is the backpropagation, I will be able to update, to check all to calculate the gradients in terms of the initial inputs that I have. Okay, so there are different ways of estimating the error. For example, we calculate the norm 2 between what I'm supposed to get and what I get from the forward method network. Or the negative log likelihood, again, is just to estimate, to see the difference, how far, what is the distance between what I have obtained and what I should obtain based on the training set. So this is somehow sometimes called the cross entropy. So it's just a way of evaluating the output. And from there, what we need to do is just to check the gradient, and then we have to do the backpropagation. Okay, I wanted to just illustrate this. I hope the notations are not too scary. But let's say I have, this is my input. This is the matrix representing the weights, because this is 2 by 2. So I need 2 weights from here. I need 2 weights over here. That's why I have to use a matrix 2 by 2. And then for each of them, I need one bias. So I just call them BI1 and then BI2. So these are the initial weights that I could just set randomly. Okay. The next stage, I need to check the activation function. Some of the classical activation functions, for example, the ReLU is just defined as the maximum between 0 and x. So we just take the positive value. Okay, so but it's just a function. We can apply it to whatever is coming over here once we apply the weights and then the bias, and similarly over here. Okay, so this is at this level. Now the output, again, we apply a set of weights and then some bias. So again, we have 2 by 2, and then we have 2 bias, BH1 and BH2. Okay, until to the next level. And at the end, if it is just a classification I want to do, then I just use the softmax for the final one, where, as I mentioned previously, shown previously in the slides, it is defined by just exponential, or let's say, or 1 in, and then we have the sum of the exponential on the denominator. So once I'm done with this, I will get some probabilities, okay, which will tell me where these, I mean, the input that I have, where it should belong based on my calculations. I have some numerical values, but I will not bother you too much with this, I will just briefly just show how it works. So this is, let's say, the input. I just set some values. And this is what is expected to obtain. We are supposed to have, let's say, Z1 and Z2. We should get these numbers. That means we have, let's say, 2 classes. So this one belongs to class 1, okay, because this one will represent the probability. But once we are doing the forward, let's say this is what we get at the end of the forward. Just let me just go back for a while. Okay, so this is once we do the forward method, forward propagation, we are over here, we obtain some values. We need to check the output, compare with what we are supposed to get. Okay, so we need to compare this one, 1 and 0 with the output that we are getting from the forward propagation. Okay, so as I mentioned, the weights could be just set to any numbers. So I just set some numbers. The bias could be any number as well. The cross entropy, if we use the equation, then we obtain just by using the formula, minus Z1 log Y1 and so on. And we could find the average by just looking at the overall error, if I could say, the overall error between, for the data that I have. So for example, just say E equals to half of the sum. Okay, again, I will just to highlight quickly. So what is done in this case, the output, the E1, I have to differentiate because it's all depending on the weight WH11. I will just show quickly what we had over here. This is the WH. The output over here is something depending on these parameters. So that means the output, I could just differentiate it, with regard to all these terms that I have over here. Okay, so we can do all the derivatives. Now, once we have this, what I wanted to highlight actually, which is the learning rate. So once I obtain the output, I mean from the gradient, I would like to update the WH, which is the matrix of the weights that I had at the level before. So how to update it? This is where you apply the learning rate, which is a parameter that you have to fix. If you fix it too small, then it will take long time to reach the result that you want. If you get it too big, you might lose the point that you are targeting. So it has to be set appropriately. And using the learning rate, by applying to the gradient that you obtain over here, you can update the matrix of the weights. So that could be, for example, the update for this example. And we could do the same thing until we go back to the initial weights at the initial level, and do again the forward propagation and compare the result obtained with the result that we should obtain. So we can keep going forward, backward, until you obtain something which is satisfactory in terms of error, the difference between what is expected and what is supposed to be obtained. Okay, so that's the principle. It's just good to see it again, maybe at least once, but that is how it works. And if you have a network and you are able to set the learning rate, I mean, appropriately by doing, trying, for example, different values, at the end you can get something which is good enough. So in that way, when you obtain a new data, you should be able to classify it correctly. Okay, let me check if there's any. Okay, next. Okay, now from fully connected, you would like to move to convolutional neural networks. So how it works, let's say I have an image, but you will notice that this image have a kind of depth. Okay. We'll see later on why. When we do the convolutional layer, we need a kernel. So how it works, I have, for example, over here, I will have a small matrix, let's say, for example, 3 by 3 or 4 by 4, 4 by 4. I will have to do it to compare, I mean, to calculate the products, the pixel that I have here compared to the pixel that I have in my kernel, and then I do the sum of all of them, and then I will have to store it in a new matrix. I will show it later on how it works, but that's the principle. So I have to scan the image. I start by, let's say, the left corner, the upper left corner, and then I will move to the next pixel, and I do the same thing. If I start with a matrix 3 by 3, then I just calculate all the products, and then I store it in a new image or a new matrix. Okay, so this is when I move in the right side to 1 pixel, I will calculate, get the value, and store it over here. And I can do this for the whole image that I have. At the end, I obtain a new image, the result once I do the convolution with a given kernel. For example, we start with an image 32 by 32. Okay, that's the dimension. And I was talking about the thickness over here is just represent the 3 colors, let's say red, blue, and green. So I will have a thickness. That means filter over here, W, should have the same thickness. Okay, so I will have, for example, 5 by 5 by 3. So I have a small matrix, 5 by 5, but it has a thickness based on the thickness that I have here, which is 3. And I could do the convolution. I start with the upper left corner, and I just keep moving until I finish scanning the whole image. So I will store it. I will get a new image for each filter that I use, for each filter W. Okay, so if I have this one as an initial image, I look at something like this. This one, if I use 6 filters, that means each filter, when I apply it, I will get a new image, which is called the activation map. And then the filter number 2 will give me another activation map. I can just stack them to obtain a kind of volume. Okay. Now, if you notice over here, we start with an image 32 by 32. But since we are doing the convolution, we are losing because of the corner. If I at the extremity, I will not have anything above. So that means I will be losing. That's why at the end here we are getting a size which is 28. Now, to avoid getting, because if I keep doing this, losing this in terms of the size, I will be getting a very small image. If you don't want to do that, then we could just add some zeros around this value, and we could add the number that will fit us to get the exact dimension that we had at the beginning. Okay, so it could be by doing mirroring the point that we have here, or just adding some zeros, so that the dimension will be just maintained to 32 for this case. So we can do this. This is, let's say, when I have 6 filters, I do the convolution. I obtain this volume. This is how it looks like. So I have one filter. Let's say here the red filter. I just scan the whole image. I will store it. I will get a feature map. I take another filter, the same dimension. I just scan. I will get another one. So at the end, I can just combine all these images, and that will be the volume I obtain after the first set of convolutions. Okay, so let's say this is the output, but over here I could do the same thing. I just need to find filters with the same depth. I could apply the same thing. I will get another level, which will represent the convolution by using different set of filters. Okay, and in that case, actually, I could even do it in just 1 pixel, because I just need to have 1 pixel with a certain depth. Then I could just multiply all the terms and just store it in a new matrix. So that's the idea of convolutional neural networks. So we can, using this method, we can just do it a certain level, exactly the same way as neural networks. And from there, we can get some information, again, by looking at the different filters that I have used and how to improve to analyze the image that I have at the beginning. Now, what people have been doing is, based on this basic principle, people have tried to build some, to construct some architectures. So what I would like to show in the next slides is that what have been built by using this idea and how it is used in practice. So I just use some of them. The most famous, probably the first one is the Net5. So over here, I just want to highlight some of the numbers that are used over here, because definitely the higher you have in terms of number of layers, then in terms of calculation to be stages, it will be more complicated. You need big machines, but definitely in terms of a result, you can expect bigger results. Better results. Okay, so here they use filters with size 5 by 5. There are just a few characteristics. LeNet is probably the first one that was implemented, and it showed huge result in terms of, for example, image classification. Okay, so just to highlight the number of connections, and then this is the number of trainable weights. So these are the weights that are used for building the system. The ImageNet. So people were just asked to send any kind of image with labeled. So could be not necessarily medical, natural images, bicycles, cars, and anything. So at the end, I have like 1.2 million training images and more than 1,000 classes, actually 1,000 classes. So this is ImageNet that was given, if I let me take like a prize for this challenge. Okay, then later on we have AlexNet, where we have the max pooling, the ReLU. We talked previously about ReLU, which is one of the activation functions. So we see how it is implemented in terms of what are needed, the GPUs like implementation, 50 times over the CPUs. And this is just to illustrate that it is huge networks that were built by the same idea of convolutional neural networks. The VGGNet, this one, instead of using 3 by 3 or 5 by 5, use one 7 by 7 filter, and the others are 3 by 3. And just now I was mentioning about the one by one convolution, because once I have a volume which is from, let's say, the first layer, then I could just use one by one because I have a thickness, so I could still do the convolution with 1 pixel. ResNet is the next one. So again, we have big numbers over here, but just to highlight some of them, still using 3 by 3 convolution. You have like 256 feature maps. So feature maps is the one you obtain once you implement the filter. And we are at 600,000 operations. So it's huge. And as VGGNet, it uses as well the one by one convolutions. Now, what is done with all these things? I just highlight two of the most used in this case. In terms of, I have, for example, the ImageNet, which was based on just natural images or any kind of image. We have 1,000 classes. Now, if I have, let's say, a medical application where I want to do a classification, how to use these architectures to do the classification without having to build it for my own application, just riding on what is already published, already implemented. Now, this is a very good idea that is used in this area. So we use outputs of one or more layers of a network trained on a different task as generic features detectors. We train a new shallow model on these features. So what does it mean? So for example, over here, I have, let us say, for example, the ImageNet. So all the weights that I have at a certain level, they are based on the natural images or the images that I have in this data set. But even if I want to do classification with medical, the weights I obtain over here could be still useful, because if you could say, for example, an edge is still an edge. Doesn't matter if it's coming from medical image or coming from natural images. So that's why the idea of transfer learning, whatever the system has learned at a certain level, we can just get it over here. Then we use it for doing the classification of the data that I have. Because in that case, at the end, for example, if I just use SVM, as you have seen, for 2 classes, I will be able to do the classification accordingly. That means we are just riding from the features that are obtained from these networks, I mean, these big architecture, but then we implement them in the data that we have. So this is a very good idea, and it saves in terms of building your own architecture, which could be very expensive. Now, to improve this, we talk about fine-tuning. Now, if I just take the features I implemented on my images, it may work, it may not be enough. So then the next step for fine-tuning is that we want to do a certain number of rounds of forward and backward propagation, because I want the system to be more adapted to the data that I have. So I don't just use the transfer learning, but once I have the features, I still do a few of forward and backward. Or a simpler way to say it is that once I get the good features, that means if I do the classification for, let's say, medical images, after obtaining the features from the ImageNet, for example, to be able to make sure that it works very well, I mean, it will write the features for my data set, I will do again a set of forward and backward. We have seen it before. So if you do the backward, that means you are trying to improve the ways that you have. So I don't start with just random values. I start with some values from the existing architecture, but then I have to improve them based on the values that I have, I mean, based on the data set I'm trying to classify. So that's the fine tuning. Okay, let me just check. Medical image segmentation. Yes, I'm going to talk about segmentation after this. Yes, that one will be covered in the next slides. Watershed, O2, etc. Okay. The correct approach, is it possible in MATLAB? Yes, MATLAB is possible, but definitely right now I would advise for Python. Python, there are many algorithms that are well established, well developed, and available for everyone. So it just needs a step to learn it, but it's not that complicated. And nowadays you can find a lot of resources on with Python. CNN model to use as optimization model to minimize the given cost function. Can we use CNN model to use that one? I'm not sure if it has been implemented. So we use CNN model to use as optimization model. To minimize the given cost function. Well, actually, all this implementation, as long as I have the data in like the training set, then probably could be implemented in optimization models. But I'm not sure I get right this question. But in all cases, if I have any model, I mean any problematic where I have training sets, then I could implement CNN and see how to estimate, or let's say to do classification, for example. Okay. Okay, so that is all for how the architecture can be used in transfer learning or fine tuning. Now, let's talk about segmentation. So this is one of the other big work that is in the area of medical image processing. So in one hand, we have the classifications, but in the other hand, we have the segmentation, which is very common. That means I have an image. I would like to see what are the different portions. If there are some abnormalities, I need to find where they are. So that is something as well highly useful in this area. Now, there are too many applications that have been developed, especially recently. I will just highlight some of them. Now, the first one is the fully convolutional neural networks. So this was done in 2015. The idea over here is that there is no dense layer. That means we just have from the beginning until the end is just convolutions. We just do the fully convolutional co-convolutions until the end. So if you can see, for example, over here, we just use the backward learning to go back. So we have the size represented over here. Either it goes down, because at the end, what is done is the pixel prediction. That means for each pixel, I need to get a class. Okay? So that's the idea of FCN, and it is again not using any dense layer, and it has to be done at even pixel level. Okay, at the end, we want to classify each pixel of the image. So at the end, we get the pixel that belongs to same class. Then we have some colors to represent it. The UNet is again using one by one convolution, but it is specifically built for medical applications. This is somehow to solve the problem of data size, because sometimes you are dealing with different size of data. So this system, I mean, this architecture will allow actually to use different sizes and using some patches to be able, but it's still based on one by one convolution, and it doesn't use any dense layer. And the name is coming from this shape, which is a U shape. This is widely used in the medical area. Another two segmentation methods. We have the SegNet, deep convolutional encoding and decoding architecture. So this is mainly based, you can look at the image over here, it's fully based on encoder and decoder. Okay? And we only have one softmax. If you remember, the softmax is the one giving something like the probability at the end. So again, it will give for each pixel what is the probability that it belongs to a given class. So we can have a map, and then we just combine those belonging to the same class with one color, for example. So that's for SegNet. And the last one probably I would highlight over here is the mask RCNN. So this one was very interesting in the way, sorry. excuse me. So we have the the mask RCNN. The way it was done is by different levels. Initially, we have the RCNN, and then it was improved in terms of the speed of the calculation. So to faster RCNN, and later on the mask RCNN was made. At the end, this one as well works in terms of pixel classification. So initially, sorry, initially you have some binding box. You have some box for different elements. That was the initial idea actually of RCNN. But then it was improved in terms of finding the class of each pixel. That means we have to improve in terms of the boxes that were given to find the final classification of each pixel. Now, to finish with these networks, I just mentioned these two. Have the RNN and then the LSTM. So the RNN, how it works, we have a network where when I have the output will be feedback to the input for the next level. That means I need to use the information of the output. I have to use it for the next level. So if you represent it in this form, let's say it's just like we open it, and it will be something like this. So at level t equals to 0, for example, I have the output h0. But I need this output. I will combine it with the next input, which is x1. That means the h1 will be depending on x1, but as well uses the information from h0, and so on. So it just continues the same way until the end of the, let's say, the network. So it was well defined. The only thing is that it suffers from a problem which is called the vanishing problem, the gradient vanishing. That means if the gradient are going to 0, then it will be very difficult to have some updates. So to improve the RNN, the LSTM was created. The same thing, it uses the previous, but it has a forgetting factor. That means if I keep adding the previous knowledge from the previous networks, how much I need to keep for the next stage. Because at a certain time, you cannot just keep accumulating all, for example, from h0 until let's say 7, then maybe the information that I have at h0 is not useful anymore. So I need to find a way to forget those parts and just keep the one that is used. So that is the LSTM, and it gives better improvement because it doesn't suffer from the gradient vanishing problem that is in RNN. Now, these two are mainly used, a lot used in time series, for example, because it's something over the time. I want to see, for example, how to predict what will be happening next based on what you have in the previous stages. Okay, I think it's time to talk about the applications. So that is the last part. I have selected a few based on the interests of the groups I'm dealing with. Now, the first one is the knee osteoarthritis. So I will just say OA. It's easier for me for the pronunciation. Now, what is happening here is that you have a cartilage between the two bones. So this has a certain thickness, but sometimes the thickness is getting low, and it's getting low, so that will give some issues, some problems. And the two main things that are done over here is that how to localize it in an image, and then how to estimate the thickness, because you need to estimate the thickness to see if it is normal. There should be a certain thickness, and the level of abnormality will be graded. Now, the gold standard is just to use the X-rays, and it has some disadvantage. First, as shown over here, This is a 2D. Here we don't have really a volume, so the evaluation is done with 2D images. So we have some variations, I mean, intra or inter grader. So for example, two doctors could give different grading depending on what they experience, for example. So it is in general quite difficult, and in terms of clinical applications, is challenging. So the scores, as I was mentioning just now, for saying the level of abnormality is called the KL score. Now, this data set is a huge data set, which was freely available until, I guess, 2 years ago. Currently, it seems not available. We have tried to get it. Recently, we're not able. So from US, we have the most multi-center osteoarthritis study, and then we have OAI. So these are the number of images, and these are the levels from KL0 to KL4. KL0 means the normal, and KL4 is the worst scenario. Okay? So from the images, need to see how to localize automatically the cartilage. And then the second work over here is just to see what will be the way to get the grade of these images based on this KL grade. So this was a work done in this area. It was 2017. So what they have done, they have implemented the FCN. Just now when I talk about the segmentation, that was the first one I mentioned, the fully convolutional neural network. So localization of knee is done by using the FCN. So this is the network they have built, and you have the different colors. For example, the convolution is just in pink, and we have the max pooling, upsampling if you want to get the size of the image, and at the end you have the classification. So using this, they were able to get the localization to find exactly where is it the cartilage in general. And then the second work was to find what is the grade of each image. So find first, localize first the abnormal, I mean the cartilage, and then do the grading. So for the grading, they have done this architecture where they have different convolution with different sizes. Over here, you can see the 32 times 11 times 11, the pooling and so on, combination of several. And at the end, they will get output, which will highlight what is the grade from 0 to 4. Now, this is one of the successful implementation of deep learning in this area. And before that, the best result were obtained by using this method, the weighted neighbor distance, using compound hierarchy of algorithms representing morphology, which is a kind of ensemble algorithm. That means looks at the output of different classifiers and takes the best. Now, somehow that was the benchmark at that time, and you could see over here the results. The benchmark for accuracy was about 29 for the OAI data set, and for most it was 34, which is very, very low, okay? Relatively low. And you have the mean square. But once they implement this deep learning, first they have done, both of them, first they have done the fine-tuning. Fine-tuning, as I mentioned previously, is just we get the values from existing architecture, but then we have to do the fine-tuning. That means we make a few rounds of forward and backward, and to adapt to the data set that we are dealing with. So when they do that, they obtain 57.6%, which is compared to the others extremely high. And when they build the network from scratch, that means without doing the fine-tuning, just building the network by itself, they even improve the results. Now it is 60%. So this one shows just how using deep learning improve the result for this particular case. It's somehow like double the percentage in terms of accuracy. So that is in terms of localization. And similarly, in terms of grading, so we have here the manual localization, and then we have the different grades from 0 to 4. the automatic localization was giving, for example, if you just look at the precision, the average over here is 0.57, and the manually done is 0.60. So it's very close to what a human would do in terms of grading. So which is exactly a very good output, a good implementation of deep learning for this case. Okay, so that's the first application I wanted to highlight. I have some students working on this. It's very challenging, but hopefully we'll get something. The next one is the age-related macular degeneration. So an acute vision loss due to retinal capillary leakage in the retinal swells. So this is one disease. So as the name mentioned, it is age-related. At a certain age, this thing could happen. It's very challenging to diagnose, to do the diagnosis using fundus images, mainly because the information of the depth is not there. So if I have the information on the depth, then I could probably estimate to see how, what is, for example, the volume that is there in terms of leakage. Now, what people have been doing recently is just to use the OCT, the optical coherence tomography. This is for detection or segmentation of AMD. I will show later on the next slide. They have different types of liquids that could be leaking. So each of them need to be evaluated in terms of estimating the volume. So from there, it will give to the medical doctor a way of knowing how bad is the disease at a given stage. Okay, so that will be a good thing to assist the ophthalmologist for grading this disease. Okay, so as mentioned over here, people have been using machine learning techniques, and recently as well the CNN, for finding for localizing the leakages that are leaking. Okay, so these three are the ones that people in this area are looking into. That means intraretinal fluid, the IRF, the supraretinal fluid, SRF, and then the last one is the pigment epithelial detachment, which is PED. So these are possible leakages that could be having leakage. So once they have, the objective will be sorry, to estimate how much is there. I mean, evaluate the volume, and that could be a good feedback to the medical doctor. So I just highlight one of the recent publications in this area, where what they have done is just the automated layer segmentation of retinal. Again, he's using OCT. So they have used a deep feature enhanced structures with random forest classifier. So this is one of the classifiers that I have in the table previously. But somehow it's not fully the classical machine learning, because they have some deep features, but at the same time, they combine with some other features and to do the classification using random forest. Okay, as mentioned over here, it's an integration of deep features with hand design features. That means features that we just extract, as I mentioned at the beginning, the different ways of finding different features. And if you know exactly the different problematics in your particular case, you may have an idea about what feature will work. So probably this is what they have done over here. And at the end, they have used the random classifier, the random forest classifier. So they have achieved an F-score of 0.885. Now, what we have done in this work, we have used actually this data set. These are some data sets that are existing. Some, the training and testing are available. Sometimes only the training is available, the testing is not available. That means once you have, you can just work on the training, because the testing is kept by the owners. And it's another data set which is Optima. So we have training and testing, but both of them are available. So this is one difference. We have two different data sets. Another difference over here is that what are the devices that have been used, because these devices, they have some parameters. and the type of image that you obtain at the end might not be the same. So that makes it a bit challenging in terms of if you want to compare different methods. If they have used only, for example, this device, then you need to use exactly the same data set, to be able to compare. Now, what we have done in this work, this is a work that was published recently by one of our PhD students. So we have SD OCT volumes. The main idea over here is that instead of using the whole image artist, we look at the patches. So if I concentrate on the patches, we expect to have better results because we just look at locally, and adding some pre-processing. That one is somehow done by everyone. So resizing, denoising is classical way of doing it. The architecture, if you notice here, we have a few that I already mentioned: the FCN, the SegNet, and the UNet. And there's one more, which is Deep Lab. So the idea was here to see, once we use the patches, what will be the effect on all these architectures. And the last step is just to add a kind of filtering for the post-processing. And at the end, we have the segmented image. So the classical way of comparing the result could be the dissimilarity coefficients, which is defined here with this formula, where TP will be the true positive, Fn will be the false negative. And you obtain a result of 0.85. So as I was mentioning, we have different types of data sets. So here just a few highlights of the type of result that you obtain. So 0.92 using this particular data set, and then using the highest average was obtained by using with 0.84 for DSC based on the series data set. So that was a work published just a few weeks ago, where again the main thing was just how to use the patches to improve the segmentation. Okay, let me move to next. This is the chest X-ray images. Now, what is happening is that in terms of purely image processing, we just want to find abnormalities. But there's something else that is needed somehow in this area, is that to generate a final medical report. For example, the medical doctor could just write a few items over here in terms of, for example, comparison, indication, findings, just a few, which are not really full sentences, but just a few group of words. Okay, an impression, for example, here just a few group of words. But to be really useful for the next or the person who will be receiving it, it would be better if they have the full report. That means a full medical report describing whatever is in this image. So it's just adding to the image processing something like not really text, but generation of a report generation. So it's challenging, but it's very interesting, because if this one works, that means at the end you have a system, the image comes in, and just output will be the localization of the abnormality. But on top of that, you will have the report of like a medical doctor would do by writing a full sentence. So once you have this kind of system, there are many ways of evaluating evaluation criteria. But I just mentioned two of them over here. This is probably the I will just call it blue. A bleu actually is means blue in French. It's just to a statistical metric for checking how good is the report based on the let's say the original report done by the medical doctor. And another one, which is the rouge, which means red, recall oriented and the study for distinct evaluation. This blue I will show it later on. It has actually different levels. You have blue 1, blue 2, and so on. So this is classically used for estimating how good is your output in terms of generating a text or generating the report. So this is one of the data sets which is available that could be used. It's just a data set of X-ray images, and you have some reports or short reports, and you can work on it to generate a full report. One of the probably the first work in this area was just 2018. So what the authors have done is to generate a multitask learning framework to prediction of text and the generation. So the text is just the small group of words that a medical doctor would write, for example. Now, the idea is just first to generate these text. Once you get the text, then from the text, you want to generate a full report. The text will be just a few group of words, as I mentioned. So they look at the co-attention mechanism to localize the regions containing abnormalities, and generate narrations of them. The co-attention is that if I have an image, I want to look at some particular places. So not the whole image will be interesting, but what are the places where the image, the medical doctor should focus to see some abnormalities. And then associate this to a few group of words. So at the end, they have just used the hierarchical LSTM, which will be used to create a full sentence or full report, just like generate long paragraphs based on the small groups of words that they have. For example, if you combine the text, how to combine them in a meaningful way, which is a bit challenging, but there are ways of doing it. Now, for us, what we have done, similarly, we have a group of words. We have the chest X-ray images. We have done what we have called the context level visual attention. So again, we want to combine whatever is the output, for example, from a CNN. This is from the image point of view. At the same time, we would like to combine this with the images. The text. Okay, so this is the original report for a doctor. So you would like to combine this and get the features, and these features should be representing both the abnormalities in terms of image and the keywords that I get from the report. The next stage is to apply the LSTM I just mentioned just now. For the previous work, they applied the hierarchical LSTM because that will help them to make full sentences. Sentences that have meaning. So we have done something similar, and at the end we can generate a report. So this is how it looks like. So these are the X-ray images. This is the original report, and this is what is generated by the system. And then we have to compare, and we get a few values, as I mentioned, in terms of blue, in terms of blue, and rouge. These are the criteria. This is the results that are obtained. I just highlight over here the MHMC. This is the work I mentioned at the beginning. This is probably the first work. Some people have done some improvements. The last 3, 4, 5, 6 are just our implementation with different combination, just looking at how to improve the results. In a few criteria, we're able to get better results. But in the blue one, which is one of the first one that is checked, unfortunately, we are not able to beat the competitor, if I could say. They're getting 0.517, we're getting 0.5, and we're still working on it to improve. But some other criteria, the results that we obtain are somehow much better. So this work was done with one of my collaborators who is in Nanded University in India. Okay, I need to move a bit fast to finish. So the X-ray will give me a good transition for COVID-19. So as you know, this is the way of testing COVID-19 is the PCR, which is the polymerase chain reaction. And one of the challenges, at least a few weeks ago, was the number of test kits were not that high. Maybe now it's solved in some countries, but still a challenge. The cost of the test, and then the waiting time for getting the results. So here I just highlight one article. So it is a case report of COVID-19 with false negative for the test. And this is just a way to highlight that the chest X-ray will be something highly needed in this area. So this, in this journal, they mentioned some cases, and not only in this one, some cases where the test was negative. That means saying that the person is fine. But then when they look at the chest CT, some abnormalities were there. So it was positive. So you'll be surprised, but in a few 2-3 months, a lot of people have published in this area. because this is something new and people have like way of accelerating the reviews and publishing. So I just highlight here one of them, which is automated detection of COVID-19 using deep learning. And in that paper, they highlight a few other works that have been published recently. A few of them, they have used the transfer learning. Okay? You can see, for example, here we talk about ResNet, and there are some networks they have implemented. They have implemented. And over here, this is the size of the data sets that have been used. Okay? So 175 and so on. Now, the results are somehow high in terms of accuracy, up to 98%. But definitely, it gives some promising results. But looking at the size of the data set, it is not fully convincing in the sense that more data are needed. And the other challenge that is there is that, as probably you have heard about the asymptomatic cases, where, I mean, for example, the first case I mentioned just now, the person doesn't show anything, but actually the person has the disease. So in terms of images, that is something needed in terms of many samples of asymptomatic cases, so that when you build your system, let's say for classification, it will learn from these asymptomatic cases and be able to detect the new ones. Because otherwise, it's quite challenging to have a system that will recognize these asymptomatic cases. Okay, I think I will go to the conclusion. So the conclusion that I could highlight over here, that I just wrote over here jump, but we could say there is a big jump when we move from traditional machine learning to deep learning applications. Because if you can see, for example, in some cases, the accuracy will just double just by moving from the traditional machine learning to the deep learning implementation. And even in some applications, the deep learning has reached the same level of human performance or even greater. And this is definitely, I mean, needed in terms of performance. The last step probably I could highlight is about the understanding the decisions. So it's still somehow a black box because you have a huge network, you have input, and at the end you have the output. But how the decision of machine learning, of deep learning in particular, is done, this is something very interesting to study, and that's why now people talk about the explainable AI. That means if I have the result from my system, I need to know why, for example, in segmentation, why the system is showing this part of the image and not another part of the image. How to explain these things? Because now, right now, it's just kind of still a black box, because you get the input, it will run, it will change the weights and so on. At the end, you get the output. Although it gives good result, but it's very good to understand how it works. I think that is the last slides. So we are about 12 minutes, so that will leave some time for questions. Maybe I can just check first if there are any in the chat. Can robot learning helpful in COVID-19? Definitely, I think so. I think it should be definitely useful in that case.
Dr. Ibrahim.
Yes.
Yeah, it was very elaborate, exhaustive, and a very detailed presentation which you have delivered.
Thank you so much, Prof. Thank you so much.
And you also demonstrated how COVID, machine learning, AI, and all these technologies can be applied on COVID.
Yes, that's right. Thank you so much, Prof.
It can, yeah, this is your certificate.
Oh, great. Very
My
nice
team
one.
is very proactive. Eh?
Yeah, very good.
Nothing else I can do from India, certification.
That's already great. That's great. Thank you so much. Thank you so
And can
much.
you just a minute, and can you show
Yes,
me
sure.
the first slide?
Yeah, sure. Sorry.
Dr. Vishal,
Ji,
This
sir.
one.
meanwhile, you can coordinate questions if there are questions.
So you request to all the participants, you can write down the questions in the chat window. Ibrahim sir, can you please share your email ID with the participants in the chat window so that
Yeah, sure.
they can contact you on the offline mode?
Yeah, sure. I will do it now.
And Dr. Ibrahim, I wanted your first screen. If you can just go back to your first page of the presentation, first slide.
Okay, let me just write my email, then I will show the first.
I think the email must also be there on the first screen. First slide, is it?
Probably I did not write it, but let me just.
I'm extremely sorry. I missed your first 10 minutes of the presentation because there was an urgent call from my head office.
No problem. No problem, Bob. I know you are very busy these days.
Yes, but very elaborate. Then after I attended that.
Yeah, sure.
Yeah, Dr. Ibrahim, mail ID is there in the chat box.
Yes.
So
I
people
just
can
show
copy
again
it from
the
here.
slide.
Very thorough researcher. Yeah, first slide, please.
Yes.
Just put it in slideshow mode. Oh, yes, please. Yeah, that's all. My job is over.
Great. Great. Okay, let me just check if there are any questions in the chat.
So there is a one question. One
Okay.
participant is asking for the medical data set apart from the UCI. Is there any link where we can find the medical data set apart from UCI source?
It depends on which kind of image, but I would mention about Kaggle. The Kaggle is very well known because they have many data sets, medical or non-medical, and it is very competitive. I mean, usually people use it for comparing the algorithm with some other methods. So in Kaggle, probably he could find a lot of data sets.
Okay. Okay. Thank you so much, sir,
You're
for
most welcome.
giving your valuable time.
Thank you so
And
much for inviting me.
it was a great pleasure to have you in the FTP. And it was a very wonderful session. How
Thank
we
you so
can
much.
implement the deep learning and machine learning on the medical analysis part. So all the participants, I request you to please connect with the sir in the offline mode. I have already shared the email ID and the Google Scholars ID of this sir. You can check the respective research area of Professor Ibrahim, and you can contact with him for any further collaborative work. That will be the outcome of this program if you do some research work with some other speakers and the resource persons. I will share the PPT. There is no problem. I will share the PPT at the end. So there is no issue. I will ask respective speakers to share their learning content to me, and then I will share with you at the end.
Sure.
Thank you so much, sir.
Thank you all.
Thank you, Dr. Ibrahim. We'll meet
Thank you
again,
very much.
please.
Thank you so much.
Thank you.
Okay, thank you. Thank you. Bye-bye.
I request you all the participants to